Pretty much the entire assignment, besides 4 problems in this section. I really don't like the fact they have it in chapter 5 because we use it so much in our last chapter. So just maybe put a note or a little star that what we're about to do will come later down the road, but they just want you to know your number sense right now. But what it's called is prime factorization.
Okay, so AJ, will this show up in like chapter 7, 8, just to kind of put a note to go back to it? Or?
Not so much this. This comes up in that last chapter that we do in chapter 10.
Okay.
Bless you.
So,
But in the rest of chapter 5, all the other stuff we do in chapter 5 shows up in chapter 6. So you
Okay.
have to be able to do chapter 5 and do chapter 6. All right. Does anyone know what prime means? I've heard Mike say it, but I remember when I asked about odds and evens and you told me it was prime. Do you remember what that means?
Yeah, it can only be divisible by itself in 1.
Okay. So prime, a prime number, a number divisible only by 1 and itself. Do you know how many prime numbers there are on our number line? Well, I don't know either. There are a lot of them. We had to do there's no proof to show how many prime numbers there are. Nobody's ever figured that out. It's worth a lot of money, though, if you figure out a way to determine it. But I don't really care. But there are a lot of prime numbers. To kind of give you some examples. 1, we don't consider prime or the other word's composite. 1's just its own little special number. That's just one of those special cases, I guess we could call it. The first prime number is 2.
1 is a special case?
Yeah, we don't consider it prime or any other, it's just a natural number. 2, 3, 5, 7, 11, 13, 17, 19, etc. This goes on forever and ever. Because if I think of the number 5, I can't think of any numbers that go into it except 1 and 5. If I think of the number 11, the only numbers that can go into 11 are 1 and 11. So 8 I know isn't prime because I know 2 can go into it and 4 can go into it.
It can only be like for whole numbers, right? Like
Yeah, we're just dealing with natural numbers.
so a decimal would have no effect on.
We're not even working with those. Yeah, they wouldn't be this whole numbers. Now the reason we talk about this is we try to break numbers down. Let me just show you an example. Let's take the number 24. Now, if you do not have your multiplication skills down pat, this is where you will be using that little chart every single day in this class, because in this chapter it's all about just knowing your multiplication skills very quickly. So the little chart does come in handy in this chapter. All right, I want to see if I can break down the number 24. What 2 numbers, I don't care which pair, can multiply to give me 24?
2 and 12.
Okay, here, 2 and 12, 6 and 4, 8 and 3. You can use any pair. I'm going to use 6 times 4. I usually use the closer the numbers. That's usually the one I use because then it's usually less steps. If you want to try 12 times 2 or 8 times 3 and see if you get the same thing, you can.
Wouldn't it be shorter if you had a prime to begin with?
Well, then you couldn't do anything. You just-
No, I'm talking about with the 8 and the 3.
Yeah, but the 8 can be broken down 2 more times. So the 6 and the 4, I'll just have to break it down a little bit. So I've broken them down. You have to keep breaking them until you only have prime numbers left. How, and the only way, can you break down 6?
22.
2 times 3 or 3 times 2 all means the same thing. How can you break down 4?
2 and 2.
2 times 2. Do we have all prime numbers now?
Yes.
Yes. So our prime factorization, and it doesn't matter what order you have the numbers in, I have a 3 and I have 3 2s. But you can have these in any order because you might have used 2 other sets of numbers. But that would be your prime factorization. And again, it comes in more handy when we're working with square roots, but they want to make sure you're okay with it now. A way you can check it, 2 times 2 is 4 times 2 times 3, and you're back to your number. So you can multiply them all together and get right back to your number.
But that's 2 cubed, right?
You could write it as 2 cubed.
Yeah,
Yep.
that's what I was gonna ask when I was studying, trying to pass the test, and the square root thing looks.
The things. Yes, you can write it like this: 3 times 2 to the third. I will accept this one or this one. It does not matter which way you write. If you see it as 3 times 2 to the cube, you can write it.
Isn't there something like 24 times 3 times 22 times 21 times 20 times 19 times 18?
It's kind of like Pascal's triangle, but we don't do anything like that. You don't even do that in trays, so.
I like that. Her face was like,
Don't have to worry about that. I'd have to study it. I don't even have it off the top of my head anymore. Okay, try 18. Different numbers you can choose from.
Does that mean the multiplication?
Yes, the box means one. Breaking down 18, you may not choose the same set as your neighbor. The book may not choose the same set as you, but you should end up with the same amount of numbers and maybe just in a different order.
yeah, that's what I got.
How would you break down 18? What pair did you choose?
6 and 3.
Okay. You could choose 9 and 2, no big deal. So I'm going to choose 6 and 3. So if I break down the 6, what would you get when you break down 6?
2 times 3.
Do not say 3 times 3. I always see that on the test. They're adding. So 2 times 3. Now this one, can you break down a 3?
No.
No. So you're just going to bring it down on the tree. I just call this doing the tree method. You just bring it down if you can't break it down. So my final prime factorization, I have a 2 and I have 2 3s. You could write it like that. That's perfectly fine. Or you could write 2 times 3 squared. Okay, so either of those answers will work. All right, let me give you a bigger number. Let's say we have 48. Lots of different pairs you could pick. I just seem to always pick the ones closer to each other, but it really doesn't matter which ones you pick.
12. Did I just say that out loud?
Well, 12 does go into that.
I had a brain fart when I was like,
And try that one.
I have a question.
Mm-hmm.
When you can see where you have the prime thing in the box,
Mm-hmm.
does it matter if you automatically just put the bigger number at the end, like 3,
Yeah.
3, 2?
Doesn't matter.
Okay.
Anywhere.
All right.
You could put 3 2 3. Doesn't matter.
We said you can use that. Can you do it?
Mm-hmm.
So if I have like,
Any set.
if I have like 5 2s in there, I can just put 2 or 5.
Mm-hmm. What pair did you use to start?
12 times 4.
12 and 4, anything else?
6 times 8.
I'm going to use 6 and 8. Again, it doesn't matter. I just usually use the one closest to each other. So 6 and 8.
What about 12 and 24?
12 times 24, though, is 48. If you think of 2 numbers that multiply to 48. 12 times 4 multiplies to 48. If I break down the 6, I'm going to get 2 times 3. Now, those are done. I can't break those any further. The 8, I can say 4 times 2. Now, what's the only thing left on mine that I still need to break?
The 4.
The 4. So I don't like, because I saw yours, I don't like my numbers floating up on the tree like ornaments. I like everything to come down because I might lose something up there. So I'm going to bring the 2 down. I'm going to bring the 3 down. I'm going to break the 4 down. So that's 2 times 2. And then I'm going to bring this 2 down. So my prime factorization, I've got, it doesn't matter what order, I could just write it in that order. I'm just going to write 3, and then I've got 4 2s. So you could write it like this. Or you could say 3 times 2 to the 4. So either of those will.
I did.
Good.
I feel like Dora Explorer.
Okay.